So today's lesson is on potential dividers. Let's go ahead and look at our lesson objectives. So by the end of today's lesson, you should be able to explain what a potential divider is and how it works. And you should also be able to answer questions related to how the potential difference across different components within a potential divider circuit vary as changes are made to those components. So in order to understand what is happening with potential dividers, we need to go back and just recap what we already know about series circuits. So there are three rules that we need to be comfortable with when we're dealing with simple series circuits like the one shown in this diagram. The first one is the fact that the current is the same in all locations. So if I have a look at that in a little more detail, we've got here 4 different locations. I've labelled the current in each of those locations as I1, I2, I3 and I4, and we can see that all of those currents are exactly the same. So we're not going to get a variation in the current at different points. It's always going to be the same. The current passing through R1 is the same as the current passing through R2 is the same as the current passing through R3 is the same as the current passing through the cell. The current is the same in all locations. The second rule is the fact that the total resistance of the circuit is the sum of the resistances of each individual component. So in this case, we've got that R total is equal to R1 plus R2 plus R3. So to give you an example, if those resistances were 12 ohms, 15 ohms and 7.5 ohms, to work out the total resistance of our circuit, we would simply do R total is R1 plus R2 plus R3. So that's 12 plus 15 plus 7.5, which gives us a total of 34.5 ohms. So that's the first 2 rules. Let's look at the third. So the third rule, and probably the most important for today's lesson, is the fact that the potential difference provided by the cell, what we call the EMF, is shared between the components in the circuit. So if I label this up as V1 being the potential difference across R1, V2 being the potential difference across R2, etc., we can see that the total voltage provided by the cell, VT, is equal to V1 plus V2 plus V3. It's probably worth pointing out here that it is not shared equally. It would be if the 3 resistors were identical, but you're never going to get a question in an IGCSE paper where you've got 3 identical resistors in a series. The PD across each will depend on their resistances, and we're going to look at how we would be able to calculate that in the next slide. So we've got here an example. Like I say, we've got 3 different resistances. In this case, we've got a cell with an EMF or a potential of 36 volts. We've then got 3 resistors of resistance 1.2 ohms, 1.5 ohms, and 1.8 ohms. Now, the question is to find the PD across each resistor. So we know that the potential difference across each add up to 36, and we'll be able to use that as a check at the end. But how would we actually go about working out the potential difference across each? Now, you should have already done this. Mr. Baker puts together some very interesting videos that you should have watched already. So this is just a bit of a recap, but I do think it's important that we just revisit it. So there's a couple of ways of doing this. I'm actually going to go through 2 methods. The first one is to work out the total resistance to start with. So we're going to use the relationship RT is equal to R1 plus R2 plus R3. So we're going to add together 1.2, 1.5 and 1.8, and we're going to get a total resistance of 4.5 ohms. So the total resistance of this circuit is 4.5 ohms. We know that the total potential difference is 36 volts. So how do we work out the current? We use Ohm's law. And Ohm's law obviously is V is equal to IR. And obviously we're trying to find the current, so we need to rearrange that into the form I is equal to V over R. Go ahead and substitute our values in. So that is going to be 36 divided by 4.5. Plug that into a calculator and we're going to get 8 amps. So we have got 8 amps passing through our circuit. How do I now use this information to work out the potential difference across each of our resistors? We again use Ohm's law. So I'm going to start with V is equal to IR. Now in this case, I'm going to use it for this resistor here. So that resistor, the current is 8, because remember the current is the same at all locations, and the resistance is 1.2. So we're going to get 8 times 1.2, which is going to give us 9.6 volts. Let's do exactly the same thing for this resistor here, which has a resistance of 1.5 ohms. So again, V is equal to IR is 8 times 1.5, which gives us a voltage of 12 volts. And then finally, we're going to do it for this resistor here. Exactly the same thing. V is equal to IR. V is equal to 8 times 1.8, and that comes out to be 14.4 volts. Now, like I say, really quite a good thing to do if you ever do this in an exam is to double check that those three voltages add up to the 36, because this is one of our rules. VT is V1 plus V2 plus V3. Plug those values in, and we can see that 9.6 plus 12 plus 14.4 is indeed equal to 36. We are correct. So I said there were two ways of doing this. I'm going to run through this second version. It doesn't matter if you can't do this. This is the way that I personally always think about components in series. I find it easier to do it. Mathematically, the two methods are actually identical. It's just thinking about it in a slightly different way. So the way I think about this is the fact that the PD is shared in the same ratio as the resistances. Now, in your maths, you have definitely done sharing in a given ratio. So that's effectively what we're going to do. We're going to share our 36 volts in the ratio of 1.2 to 1.5 to 1.8. Now, I'm being a bit naughty here in terms of a mathematician would never say or mix your ratios and decimals. So they, I'm sure, would probably say a ratio of 12 to 15 to 18. But actually, then saying that, that's then not in its simplest form. So what would they say? They would say a 4 to 5 to 6, wouldn't they? But either way, we're not in a maths lesson, we're in a physics lesson. So what I'm going to go ahead and do is just add these three up and work out how many parts there are. And if we do that, we've got 4.5 parts. So 1.2 plus 1.5 is 1. Plus 1.8 is 4.5 parts. So we're saying that 4.5 parts is equal to our 36 volts. So I now want to work out what one part is. Now, how do I do that? I divide both sides by 4.5. So I get that one part is 8 volts. And then I just need to go through and work out how many parts each thing gets. Well, this gets 1.2 parts. And so we get 8 times 1.2, which is 9.6. This one here gets 1.5 parts. So that's going to be 8 times 1.5. And this one here gets 1.8 parts. So that's going to be 8 times 1.8, which is 14.4. But most of you will be thinking, well, this is identical in terms of the maths we've done, and you're absolutely right. But it's just a slightly different way of thinking about it. And you'll see why I like doing this when we come on to talking about potential dividers in a second. One thing that I really need to stress, and this is the reason Dr. Cook doesn't necessarily like teaching a ratio method, is because you cannot apply this to parallel circuits. I mean, it is just so much more complicated with parallel circuits. So please do not try and use ratios for parallel circuits, because you will just end up confusing yourself. Only ever do it for series circuits. So moving on to the main focus of our lesson, and that is potential dividers. Here I have a relatively simple series circuit with two resistors, R1 and R2. And I've also got an output connected in parallel across that R1. Now, it's really important that we think back to the rules of parallel circuits, which we've already covered. And the key one that I want you to remember now is that the potential difference across this resistor is going to be equal to the potential difference across this output. So when we have two components in parallel, the PD across them is always the same. So whatever the potential difference is across R1 is equal to the potential difference across the output. Now, I've written that down here. I really want you to get this into your notes, so make sure you've definitely got this into your notes. The stuff we've already done, if you've added it in, brilliant. But if you haven't, don't worry about it. You've already got it in your notes from previous lessons. But this definitely needs to be in there. So I've got down here that R1 is in parallel with the output. Now that output is going to be some kind of component that controls a motor or a lamp or a heater. But the PD across R1 is equal to the PD across the output. So whatever the potential difference of the voltage across R1 is equal to the voltage across the output. Okay, that's the first thing we really need to understand. The second thing we need to understand is that the voltages across each of these two resistors add up to the voltage across the cell. So here I've labelled the potential difference across R1 as V1 the potential difference across R2 as V2, and we know that they must add up to VT. Now, how much potential difference there is across each of these two is going to depend on the ratio of their resistances. And that's what's key to understanding potential dividers, because if I change the resistance of one of those two resistors, the potential difference across them are both going to change. So by changing the resistance of this one, you'll notice I've now made this into a variable resistor. By changing the resistance of R2, I'm going to change the potential difference across both resistors. And hence, I'm going to change the potential difference across the output. So let's look at what would happen if I increase the resistance of R2. So if I increase the resistance, think about the equation. I'm going to write it down up here somewhere. Think about the equation V is equal to IR. If I increase the resistance, so that is this going up, then the voltage is going to go up. So I'm going to get an increase in the PD across V2. Now, if the PD across V2 is going up, what must be happening to the PD across R1? Well, remember, they've got to add up to VT. And so if V2 is getting bigger, V1 must be getting smaller. And if V1 is getting smaller, what's happening to the output potential difference? Well, remember, they've got to be the same, and therefore the output PD is going to drop. So by increasing the resistance of R2, I've actually decreased the output potential difference. Likewise, if I were to decrease the resistance of R2, let's go back up to our equation at the top here. Now, if the resistance is going down, the voltage across it is going to go down. So we're going to get a decrease in the potential difference across R2. So V2 is going to come down. And remember, V1 and V2 must add up to that VT. And so if V2 is getting smaller, V1 must be getting larger. And because V1 is in parallel, because R1 is in parallel with the output must be getting larger. So the key here is understanding that by changing the resistance of one of our two resistors, we can change this output voltage. And you do need to be able to follow through with these kind of explanations to be able to work out kind of these kind of systems. And we're going to get some practice with that in the rest of the lesson. So let's have a look at another example. Explain the function of this potential divider circuit. So here I've got a variable resistor, so that's this one here, and I've got a normal resistor here, and then I've got this output. Now, like I say, this output could be something that's going to control a lamp or a heater or anything like that. I haven't labeled that in here, I've just got it as output. But I want to know what happens when I change the resistance of that variable resistor. Now, in a question, you might be specifically asked what happens when the resistance goes up or down. But if you're not, then just explain either way around. So I'm going to say as the resistance of the variable resistor increases. So this resistor here, as we increase that resistance, what's going to happen? Well, if the resistance goes up, again, I want you to think back to Ohm's law. V is equal to IR. And if the resistance is going to go up, what's going to happen to that voltage? It also has to go up. So we're going to get the PD across the variable resistor increasing. And because of the fact that this variable resistor is in parallel with that output, if the PD across the variable resistor goes up, the PD across the output, or what I've called here the output PD, must also go up. So a lot of people then might ask, why do we need this second resistor? Notice if I look at kind of what I've written over here, I've not mentioned this second resistor once. So why on earth do I need it? Well, let's have a look at the next slide to see why. Okay, so the question is, why do we need this second resistor? Well, let's look at what happens when we get rid of it. So now, if that's not there, both the cell, the variable resistor, and the output are all in parallel. So if they're all in parallel, the PD across all of them has got to be the same. So if I increase the resistance of this variable resistor, the PD across the variable resistor doesn't change because it's always going to be equal to the PD across the cell. If this is a 6-volt cell, this is going to have 6 volts across it, and that's going to have 6 volts across it. It doesn't matter what I do to the resistance of this variable resistor, it's always going to have 6 volts across it. The only thing I'm going to change by changing that resistor is the current running through the circuit. And actually, when I say the current through the circuit, I'm actually only really talking about the current through this main top loop here. The current through this loop is always going to stay the same. So, like I say, by removing that second resistor, we've completely changed the way that this circuit operates. So, coming back to my my workings over here, I've said that the resistance to the variable resistor goes up, the PD across the variable resistor stays the same, and therefore the output PD stays the same. We are not changing anything by changing that variable resistor. All we're doing is, like I say, changing the current in that top loop, but it makes no difference to that lower loop, i.e. the output. Okay, so I want to talk about a specific type of potential divider called a potentiometer. I'm going to show you a video in a second of a potentiometer, or it's actually a rheostat that's set up as a potentiometer. I know you've already seen this in the past because Dr. Cook used one in his diode practical that you have already completed. So with a potentiometer, we don't actually use 2 resistors. So I'm going to get rid of those. I'm going to replace it with a single resistor that has a sliding contact. So this this here is actually a sliding contact that we can move left and right. Now, to be honest, you could just use a wire, or a piece of resistive wire, but when we're using the rheostat, we're going to use that kind of coil of resistive wire. I'll explain it in the video, you'll see it in a second. The best way to think about this, in my opinion, is still thinking about this as 2 separate resistors separated at the position of that sliding contact. So I've still got to the left here R1 and to the right R2. And if I kind of move this slider left and right, what I'm going to do is I'm going to change the length of those wires. So if I move this to the left, so if I'm going to move this slide to the left, I'm going to decrease the length L1, and therefore I'm going to decrease the resistance of R1. And likewise, I'm going to increase the length L2, and I'm therefore going to increase R2. Now, what effect is that going to have? Let's try and get rid of these, all these, sorry. What effect is that going to have? Well, if we move it, I've got it to the right here, just to be difficult. If the slider is moved to the right, the resistance of R1 will increase, and the resistance of R2 will decrease. Now, remember, this resistor here is in parallel with that output. And so the PD, the voltage across these two, is always going to be the same. So if I move this to the right and I increase the resistance of R1, thinking about that Ohm's law, the all-important Ohm's law, if I am going to increase the resistance of R1, I'm going to increase the PD across it, and hence I'm going to increase the output PD. So the PD across R1 and hence the output PD will therefore increase. So what I've now got is a mechanical device that I can move this slider left and right, and in doing so, I can change that output potential difference. It's absolutely crucial to electronics, because now I've got a device that will enable me to really finely control the output potential difference of a cell. And like I say, this is what Dr. Cook used in that experiment on the IV characteristic of a diode, because he needed to be able to control the voltage output to a really small precision, and so a variable resistor was the only way that he could do that.
So this here is a rheostat set up as a variable resistor. This black coil is wound round the drum, and this slider can be moved left or right to change where this bar is coming into contact with that coil. Current flows from positive to negative, so we're going to be coming from the positive terminal of our power supply through our ammeter. That's just there so we can see what effect moving this slider is going to have on our current. We're then going to run along this bar to the slider, down into the coil, and then we're only going to pass through this section of the coil before coming out through our lamp and back up to our power supply. If I move this over to the right, the current is going to have to pass through more of this coil, and therefore the resistance is going to go up. If I move it over to the left, we're going to have to pass through less of the coil, so the resistance is going to go down. So if I turn my power supply on, we can see that as I move this to the right, we're going to be passing through more of that coil, so the resistance is going to go up, hence that current is going to come down. Likewise, if I move this over to the left, we're going to pass through less of the coil, so the resistance is going to go down, that current is going to go up. And if I move it all the way over, the current's actually going to get high enough for me to actually start seeing some light from our lamp. So just to summarize, all I'm doing is moving this slider left and right, and because the current is coming along this bar from the slider into this coil, by moving it to the right, I'm increasing the length of that coil, and I'm therefore increasing the resistance. If I move it to the left, I'm decreasing the length of that coil, and therefore I am decreasing the resistance.
So we've just seen there that we can set up a rheostat in two different ways. So firstly as a variable resistor, and secondly as a potential divider, or more specifically a potentiometer. And so why do we do it? What's the difference between the two? Well, the first one, the variable resistor, is used to control current. So by changing the resistance of that circuit, we're going to change the current passing through it. And so if I'm doing an experiment where I want to vary current, I'm going to use a variable resistor. So if my independent variable in my experiment is current, then I'm going to set my rheostat up as a variable resistor, not as a potential divider or the potentiometer. However, what a potentiometer does is it varies the output PD. And so here, rather than varying the current, I'm actually varying the potential difference across that component. So if my independent variable is voltage, or PD, then I'm going to use a potentiometer, not a variable resistor. Okay, I've got one more question before we finish. What effect will moving the slider to the left have on this motor? So, like I said, I think it's always easier to label these up. You don't have to do this, but in terms of your thought process, I always like to put a little dash line where my slider is and label either side of that R1 and R2. Now, if I'm going to move this slider over to the left, so we're going to move it in that direction, R1 is going to become shorter, and therefore that resistance is going to go down. So the resistance of R1 is going to decrease. And if the resistance of R1 decreases, again, going back to the all-important Ohm's law, V is equal to IR. If that resistance comes down, that voltage has got to come down. And so we're going to get a decrease in the potential difference across R1. Now, we've also got to remember that this resistor here is in parallel with this motor, and therefore the PD across them is always the same. So if the potential difference across R1 decreases, the potential difference across the motor decreases. So what we're actually going to be doing by moving this slider to the left is we're going to decrease the speed at which that motor is spinning. So a very useful tool to be able to actually control how fast something's operating. Okay, So what should you now be able to do? I think after watching this lesson, you should be able to explain what a potential divider is and how it works. So we're talking about a device that divides the potential. I mean, it is literally its name describes it perfectly. We're dividing the EMF, or the potential difference, provided by a cell between two resistors, and by changing the resistance of one of them, whether it be a variable resistor or as a potential divider, by changing the resistance, we can change the output PD of that potential divider. We should also be able to answer questions related to how the PD across components within a potential divider circuit varies as changes are made to those components. So you need to be able to look at a circuit and say, well, as the resistance of that variable resistor is increased, what's going to happen to the voltages across the two components, and therefore what's going to happen to the output PD. Or likewise, you need to be able to explain what's going to happen to the output PD as the slider on a potentiometer is moved in either direction. Now, if you can't do that, if you haven't understood how that works through watching this video, go back and watch it again. And if it still doesn't make any sense, please remember to get in contact with me on Thursday mornings on the drop-in sessions to ask me questions, or just drop me an email and I'll be able to kind of give you some help. Please don't bury your head in the sand. It's not a massive topic within electricity, but it is one that I want you to try and get your head around.